All right, folks, this is notes for April 2nd. Today we're going to talk about the index of refraction. We're going to talk about Snell's law. Here's the thing with the index of refraction. The index of refraction, we're going to need it to get into Snell's law computationally. Remember what we talked about yesterday about light incident on a surface will reflect at the same angle that it was incident. Well, today we're going to talk about the light that goes into the surface, that goes into the material. It's bent as it goes in. The angle by which it's bent, we find that out using Snell's law. And to use Snell's law, we need to talk about the index of refraction. So what exactly is an index of refraction? Well, first off, we need to talk about the speed of light. Speed of light in a vacuum, 2.998 times 10 to the 8 meters per second. Not just a good idea, it's the law. Well, here's the thing about it. In materials, it's not going to be 2.998 times 10 to the 8 meters per second. It's going to be something less than that, because the light is going to interact with the various atoms and molecules that make up the material. And those interactions take time. So the index of refraction actually parameterizes that amount of time. It parameterizes those interactions. So it's a unitless number. It's a unitless number n that is defined as the speed of light in vacuum, c, divided by the speed of light in material, v. So n equals c over v. N is always greater than or equal to 1. We use n equals 1 in air because there isn't enough interaction to measurably slow the speed of light. Let's look at some other materials though, because you get into glass, you get into glass, various glass types, you get into other materials, you're going to get a lot more index of refraction. Now, the index of refraction is also wavelength dependent. This is a little bit, well, really I should say it's frequency dependent, because what's going to change when you go from one material to the other? The wavelength is going to change, not the frequency. So our index of refraction is going to be frequency dependent, but we're really not going to talk about that until tomorrow. So that's when we get into chromatic aberration and dispersion, and that's the topic for tomorrow. But we're going to use a standardized value. Usually it's an average value, it's a midpoint value, for index of refraction, for generalized index of refraction for material. The biggest thing to remember though with index of refraction, n equals c over v. So n is always greater than 1 for any material other than air. And it's always going to tell you how fast light goes in the material. So with that equation, that's what you use to convert between index of refraction and speed of light in material. So now we get into Snell's law. Snell's law tells us how light bends when it goes into materials. So remember from yesterday, what characteristic of the surface do we measure all angles? What's the relevant characteristic of the surface for all the angles? Think about it, pause the video, and when you're done, when you have an answer, Start the video back up again. Okay, we're back. So, what characteristic of the surface do we use? We use the normal, the perpendicular to the surface. All angles for refraction and reflection are measured from the normal. What does Snell's law state? Snell's law states that with two materials, N1, with indices of refraction N1 and N2, at a boundary, you're going to use the same normal for both because it's a flat surface. It's the same perpendicular. N1 sine theta 1, in other words, the index of refraction of the incident of the material that it's incident from, times the sine of the angle of that incidence, equals N2 sine theta 2. So it's going to equal the index of refraction of the material it's going into times the sine of that angle. So what does this tell us? Well, we're not going to have an angle greater than 90 degrees. We're going to have an angle between 0 and 90 degrees. So our angle is always going to be, so sine increases from 0 to 90 degrees, right? We know our trig. We know what a sine wave looks like. We know between 0 and 90 degrees, sine is monotonically increasing. So if I go from a lesser index of refraction to a greater index of refraction, do I get closer to the normal or further away from the normal? Think about it and pause the video, and when you have an answer, start the video back up again, and I'll wait. Okay, I'm back. So, which way is it? If it's going from lesser to greater, then it's going to get closer to the normal. If it's going from greater to lesser, it's going to go farther away from the normal. Now, is it possible that you can end up needing to get a 90-degree angle to make Snell's law work? Yes, it certainly is. This incident angle is called the critical angle. This is the angle, the critical angle is the angle such that there is nothing that goes out, but the refracted light wave goes along the surface. So if you have N1 sine theta over N2 equals 1, that's your critical angle. That's how you find the critical angle. What happens if the angle is greater than the critical angle? Well, remember we have a refracted and a reflected part of the wave. If the angle is greater than the critical angle, if the incidence angle is bigger than the critical angle, where do you think all the power is going? Where do you think all the energy has to go? That's right. All the energy has to go into the reflected wave. This is a condition called total internal reflection. You can use this to bend light around a corner. This is what you use with fiber optics. This is how fiber optics works. So you get this total internal reflection, which is actually pretty interesting stuff. These simple equations, the simple equation of Snell's law, will handle most of your optics problems. You can use it You can use it to calculate focal lengths for lenses. You can use it to do a lot of different things. You can use it to determine where a light source is if you know the material that the light is passing through. You can also use this to find what the exit angle is going to be from a prism. And again, we'll get into some of that stuff tomorrow. Be back tomorrow. I'm gonna have a report from Miss Swihart. You guys better have behaved for her, because I'm going to be very disappointed if you haven't. So I will see you all tomorrow. Don't forget to be working on your homework. Don't forget your papers are due on the 11th. No extensions. So get your papers done. I will start tomorrow with questions. So if you've got questions from this week, have them written down. Have them ready for me. I will see you guys tomorrow.